Hello and welcome to this A-level chemistry explanation video about aromatic chemistry. We'll start by looking at the bonding and structure of benzene and also the evidence that allowed us to arrive at this structure. And we'll finish by exploring the electrophilic substitution mechanism with two specific examples that you need to know about. Aromatic chemistry is the study of aromatic compounds, also known as arenes. Aromatic compounds are known for their unique structure and stability, which makes them significantly different to aliphatic compounds, which will make up the other organic molecules that you encountered in other topics, so the straight chain or the branched or the ringed compounds that you discovered in topics such as alkanes, alkenes, and alcohols. Arenes have many uses, for instance as fragrances and flavourings, which is one of the reasons why they are called aromatic compounds. They're also used in pharmaceuticals, for instance pain relievers, antibiotics and antihistamines. They have many uses in plastics, for instance as polystyrene. They're also used as dyes and pigments, and fuels and solvents. There are a huge variety of aromatic compounds, and the one that you need to know a great deal about is called benzene. Benzene has the molecular formula C6H6, and the structural formula looks like this. And you need to know how we uncovered benzene's structure and how we moved from the proposed structure that I'm showing here to what we know now, which is the hexagon with the ring inside it. To be classed as an aromatic compound, there are three specific features an arene needs to have. Let's explore these by focusing on benzene, which is the aromatic compound that you need to know about. Firstly, it has a planar structure, which means that it is a flat molecule. Secondly, it is a cyclic compound, which means the carbon atoms are contained within a ring. And finally, there are delocalised pi electrons, which makes benzene or other aromatic compounds more stable than we might expect. One proposed structure for benzene was cyclohexane-1,3,5-triene. Using X-ray crystallography, scientists were able to provide evidence that this was in fact not the structure of benzene. It was found that benzene had 6 identical carbon-to-carbon bonds, and that the length of these bonds was intermediate between single bonds and double bonds. Whereas if cyclohexane-1,3,5-triene was the structure of benzene, there would be 3 single bonds, and there would be 3 double bonds, whereas this was not found to be the case. X-ray crystallography was also able to provide supporting evidence for the planar structure of benzene. Here I'm showing a hexagon to give us the general shape of benzene, and each vertex, that's a point where 2 edges meet, would be a carbon atom. And because the formula of benzene is C6H6, as well as having the 6 carbon atoms in the hexagon, we also need to have 6 hydrogen atoms, 1 on each carbon. And then because we've got 3 clouds of electrons around each carbon atom, that means the bond angle between each of these bonds in the 3 would be 120 degrees. And that's what I'm showing here in this enlarged section of the benzene ring. 120 degree angle between the C to C bond and the C to H bond, etc. The planar nature of benzene and all aromatic compounds is a vital ingredient that gives rise to the delocalised pi electrons as part of the structure. Carbon is in group 4 of the periodic table, so it has 4 electrons in its outermost energy level. Since it's only using 3 of these electrons to form covalent bonds, it has a spare electron. And this spare electron is found in a p orbital. Since the benzene molecule is a flat molecule, all 6 of these p orbitals are perpendicular to the plane of the ring. These p orbitals then overlap side by side, creating a continuous electron cloud above and below the ring. This overlap of p orbitals allows the electrons to be delocalised, meaning that they are not fixed to any single carbon-to-carbon bond, but instead they are spread evenly across all 6 carbon atoms. This delocalised pi system is what gives benzene its unique stability and chemical properties. And we symbolise this delocalised pi system, this ring of delocalised electrons, in benzene structural formula by using this circle inside the hexagon. So the hexagon shows the carbon-to-carbon bonding, but the circle is representative of the delocalised pi electron system. The structure of benzene was a source of great debate and research for many years. In A-level chemistry, the thing that comes up most often with respect to benzene structure is how the thermochemical evidence can be used to prove benzene structure. It was known that benzene had the molecular formula C6H6 and that it was a ring structure. And it wasn't until hydrogenation reactions were carried out that compelling evidence for the nature of benzene was provided. One proposal was a ring structure with 3 double bonds, and if this hypothetical structure was correct, it would be called cyclohexa 1,3,5-triene with 3 alternating double bonds. When hydrogenation reactions were carried out, the enthalpy change for this reaction was measured. Firstly, if we hydrogenate cyclohexene, which is a ring of 6 carbon atoms with 1 double bond, the enthalpy change is measured as minus 120 kilojoules per mole. This means that it would follow that if the structure of benzene was this hypothetical cyclohexa 1,3,5-triene, the enthalpy change for the hydrogenation of this molecule would be 3 times the enthalpy change for the hydrogenation of cyclohexene. In other words, the enthalpy change would be found to be minus 360 kilojoules per mole. In fact, when we hydrogenate benzene, we find that the enthalpy change is actually minus 208 kilojoules per mole. So this is significantly less exothermic than was expected. And the conclusion then is that benzene is 152 kilojoules per mole more stable than the proposed unsaturated ring structure of cyclohexa 1,3,5-triene. But what do we mean by more stable? Well, generally, things that are more stable because they have less energy. So the conclusion of the hydrogenation reactions could be simplified down to say that benzene has less energy than we were expecting it to have. And you can show this in a different way by showing reaction profiles for these hydrogenation reactions. If we start with the hypothetical expected hydrogenation, where we've got cyclohexa 1,3,5-triene with a certain amount of energy, when we hydrogenate it, it turns into cyclohexane, and we were expecting the enthalpy change to be minus 360 kilojoules per mole, so very exothermic. When we hydrogenate benzene, we find out that the enthalpy change is less, minus 208 kilojoules per mole. And so that means if this reaction was less exothermic, benzene must have had less energy in the first place, because both of these reactions produce cyclohexane as the product, so the energy of the product is the same in both cases. But since this reaction produces less energy, minus 208 kilojoules per mole, that must mean that benzene's starting energy is less than was expected, and so therefore could not be this cyclohexa 1,3,5 structure. And benzene then has 152 kilojoules per mole less energy than cyclohexa 1,3,5-triene would have, and so therefore it is more stable. It's very common for the benzene ring to have different groups attached to it, and when naming aromatic compounds, there are 2 important things to consider. If the benzene ring is considered to be the main functional group, you will need to use the suffix benzene as part of the compound's name. And this is necessary when you have got halogens attached to the benzene ring, when there are alkyl groups attached to the benzene ring, and when there are nitro groups attached to the benzene ring. For instance, if we have a methyl group attached to the benzene ring, this would be named methyl benzene. A chlorine atom attached to the benzene ring would produce a molecule called chlorobenzene, and a nitro group attached to the benzene ring would give us nitrobenzene. Where there is more than one atom attached to the benzene ring, we need to use the system that we've already employed for aliphatic compounds. That means that we need to use numbers and we need to use di and tri to indicate 2 or 3 of the same functional group. So for this molecule here, where there are 2 chlorine atoms, this will be dichlorobenzene. And then when it comes to the numbers, we start with 1 for either of the atoms, and then the next chlorine atom is on an adjacent carbon atom of the benzene ring, and so this would be 1,2-dichlorobenzene. And this would be the same whichever carbon atom we treated as number 1. If we had another dichlorobenzene, but the chlorine atoms were more spread out, we pick one of them to number, and this is carbon number 1, and then we count along to get to the chlorine atom using the smallest number available. And so if we went clockwise around the ring, this would be 1,5-dichlorobenzene, but going anti-clockwise, we get to 1,3-dichlorobenzene, which keeps the numbers smaller, and so we use that. And then if the groups are attached on carbon atoms opposite each other, like these 2 methyl groups here, we obviously have dimethylbenzene, but what we have specifically is 1,4-dimethylbenzene. And on this occasion, it doesn't matter whether we count our way up clockwise or anti-clockwise, we'll always arrive at 1 and 4. Then the second thing that we need to consider is when the benzene ring is a secondary functional group. In other words, one of the groups attached to the benzene ring has a higher priority. 3 common examples that you will encounter are, first of all, when we have an amine functional group attached to the benzene. Here the amine has the higher priority, so the suffix amine will be used. But we need to acknowledge the benzene branch attached to the amine, and so we use the prefix phenyl. And so this is referred to as phenylamine. Another example is when we've got a carbonyl functional group, which also has a higher priority than the benzene ring. And so this is again going to use the prefix phenyl. The carbonyl has in fact created a ketone because the carbonyl group has got a carbon atom either side of it. And so this would be referred to as phenylethanone. And that's because the branch from the benzene ring has got 2 carbon atoms in it, so we're going to need to use ethan, and then the -one acknowledges the fact that this is a ketone. So phenylethanone would be the name of this molecule. And then lastly, if there was an alcohol group branching out of the benzene ring, alcohols have a higher priority than benzene rings, and so this would be phenol. We actually break down the molecule even smaller than calling it phenyl alcohol, and we call this phenol. Benzene and other aromatic compounds tend to undergo substitution reactions rather than addition, and the reason for this is down to the stability provided by the delocalised pi electrons. And remember, this is where the 6 pi electrons spread out across all 6 of the carbon atoms, forming a pi electron cloud, which is what the circle is representing when we draw Benzene structure. And so the delocalised electron structure is more stable than isolated double bonds would be. And it creates something known as a conjugated system. And this makes benzene much less reactive, specifically in ways that would disrupt this delocalised electron structure. During addition reactions, adding atoms such as hydrogen or chlorine across a double bond would disrupt this conjugated pi electron system. And so benzene resists addition reactions, which would make it lose its aromaticity and therefore its stability. In substitution reactions, one of benzene's hydrogen atoms is replaced, but the delocalized pi electron cloud remains largely intact, and this allows benzene to react without sacrificing its stability. Conjugation of double bonds allows electrons to move freely across adjacent bonds, creating a more stable structure than you might expect. It occurs in benzene and other aromatic compounds, and sometimes in aliphatic compounds as well. When double bonds are alternating or conjugated, they allow for the delocalization of electrons, spreading the electron density across the entire molecule. Take cyclohexane-1,3-diene as an example. It has conjugated double bonds, and so it gains stability as a result of this. But it's not aromatic because despite this conjugation, this delocalized electron cloud, this molecule doesn't have a ring structure for the delocalized cloud, meaning it doesn't gain as significant an amount of stability that you would for an aromatic compound. Additionally, the full molecule is not planar as well. Now compare this to 1,4-cyclohexadiene. The conjugation that you would get from two alternating double bonds is disrupted. In these cases, the double bonds are not directly adjacent to each other, and so there's no opportunity for full delocalization. And so the molecule doesn't have the same degree of stability that you got for the 1,3-diene conformation. And so the electrons can't be as freely spread across the structure. Another good example of this would be in penta-1,3-diene, where the alternating double bonds allows the electrons to delocalize over a greater proportion of this molecule, and comparing that to penta-1,4-diene, where the double bonds are further apart, and so there isn't this opportunity to overlap, and so we don't get conjugation of the double bond. And so an exam question, potentially a multiple choice question, might ask you to pick the molecule that you would expect to be the most stable out of a set of 3 or 4 options, and you'd be looking for maximizing this opportunity for the double bonds to overlap, for the delocalized pi cloud to spread over a greater proportion of the molecule. The electrophilic substitution mechanism occurs when there is a reaction of a benzene ring. And not just a benzene ring being present, the ring itself needs to change. We can represent the benzene ring with the hexagon with the circle inside it for the delocalized electron cloud, or we can just use the formula C6H6 for the benzene ring, but obviously if there are groups already on the ring, it won't be C6H6. And what occurs in simple terms is one negative seeking species replaces another. And in electrophilic substitution, it's always an H+ ion that is replaced. Now, an electrophile, if we break that word into two pieces, is something that is negative seeking. And so really what we're talking about is something that is a positive ion or something that is electron deficient, delta plus. Why does it happen? Well, the pi cloud of delocalized electrons in the center of the benzene ring is electron rich, and therefore it attracts the positive ion or the electron deficient atom in the electrophile to itself. There are two types of electrophilic substitution mechanism that you need to know about. There is nitration, which involves concentrated nitric acid, HNO3, as our source of our electrophile, and it involves a concentrated sulfuric acid catalyst. There's also Friedel Crafts Acylation, and the electrophile comes from an acyl chloride, and we use an aluminium chloride catalyst. This reaction is very slow at room temperature, so we need to do this under reflux in the presence of a dry ether solvent. There are other choices, but it's really important that we have a non-aqueous solvent. In nitration, the electrophile comes from the nitric acid in a reaction with the sulfuric acid catalyst. And this is actually an interesting reaction as it's happening between two acids. But since the sulfuric acid is a stronger acid, the nitric acid therefore acts as a base and accepts one of the sulfuric acid's protons. And so in step 1, we end up producing H2NO3 plus, which is the conjugate acid to nitric acid's base. And we also produce HSO4 minus, which is the conjugate base for the sulfuric acid. And then in step 2, the H2NO3 breaks apart into the nitronium ion, which has got the formula NO2 plus, and this is our electrophile, and we also produce water. This reaction can be shown in 2 steps, as I've done at first, or we can combine it into 1 step, where we've got the nitric acid reacting with the sulfuric acid, as before, going straight through to the nitronium ion electrophile and the water and the HSO4 minus. In the mechanism itself, it's important to remember that the delocalised pi cloud of electrons is electron-rich. There are 6 electrons in it, 1 electron from each of the carbon atoms. And so it is attracted to the positive electrophile, the nitronium ion. And the electrophile attacks the benzene ring, and we show this using the curly arrow that I'm showing now. Now, curly arrows, remember, always show the movement of electrons, and that's what we're showing here, but we must say that the electrophile attacks the benzene ring. And the symbolism of this curly arrow is that we're showing that a new bond is forming between the carbon atom and the nitrogen atom from the electrophile. And then this moves on through to make an intermediate chemical that I'm showing here. Now, there's 2 really important features of this intermediate. First of all, the delocalised pi cloud has been partially broken because those 6 electrons have now become 4, because 2 of the electrons in that pi cloud are now involved in the bond between the carbon and the nitrogen. And so there's only 4 electrons there. And so the ring that was representing all 6 of those electrons needs to be incomplete. And so what I'd like you to do is imagine that there was a line across the benzene ring dividing it 2/3 on one side and 1/3 of the other. And so the benzene ring's delocalised pi cloud now cannot extend beyond this purple line. And so that's why I've got an incomplete circle now to show that we've got 2/3 of the electrons that we had before. Not only that, it is now positively charged. And this also makes sense from the point of view of conservation of charge, because the reactants were positively charged because of the electrophile. We've only got 1 intermediate now, and we need to conserve that charge, and we need to have a positive charge showing in that benzene ring. And so the benzene is unstable because it's positively charged, but it regains its stability by taking those 2 electrons back. And it takes them back from the bond between this carbon atom and this hydrogen atom. And so we show a curly arrow like so. And this curly arrow is symbolising the bond breaking and the 2 electrons from that bond going back into the pi cloud. And so we produce this compound, which would be referred to as nitrobenzene, and we produce the hydrogen ion that has been replaced by the nitronium ion. If you've been asked to simply draw the mechanism, you just need to show this section. We don't need to show the structure of the organic product unless we've been explicitly commanded to do so. Now, that hydrogen ion that's been replaced is far too reactive to exist by itself. And so what happens is it reacts with the HSO4 minus that was produced during the generation of the electrophile. And this produces H2SO4, which was our original catalyst. So in this way, our catalyst has been regenerated and can be used again, which is part of the definition of a catalyst. If we want to make sure that we only add one nitro group to our benzene, we need to make sure when we're warming it up in this reaction that we keep the temperature below 55 degrees C. If we go above 55 degrees C, the temperature rise means that multiple substitutions occur, and so we get more than one nitro group joining the benzene ring, and we could get as many as 3 being added. This allows us to produce all sorts of different nitro compounds that have got huge range of uses in things such as pharmaceuticals and dyes and explosives. By far the most famous nitrobenzene compound is TNT, which has got 3 nitro groups because we've had substitution occurring 3 times with this methyl benzene. In addition to knowing how the electrophilic substitution mechanism occurs, you also need to know the mechanism for the generation of the electrophile, the nitronium ion. And this is formed through a reaction between concentrated nitric acid and concentrated sulfuric acid, and it takes place over 2 steps. The first step is the reaction between the nitric acid and the sulfuric acid, where the nitric acid uses one of the lone pairs on the oxygen atom that has the hydrogen attached, and it actually attacks one of the 2 hydrogen atoms of the sulfuric acid. And this curly arrow that I'm showing here is showing the formation of a new bond between this oxygen atom and this hydrogen atom. Of course, hydrogen atoms can only have one covalent bond, and so that means the covalent bond between this oxygen and this hydrogen atom needs to break, and that's what I'm showing with the next curly arrow. The pair of electrons in the covalent bond here is being taken completely by this oxygen atom. And this leads us to 2 intermediate products. This one is effectively H2NO3+, but I'm showing it in partial displayed formula here, so you can see that we've got a positive charge on this oxygen, recognizing the fact that this oxygen atom has used one of its lone pairs to form a coordinate bond here. In addition to that, the other product is the HSO4- ion, negatively charged, because this oxygen atom took both electrons from the covalent bond that it had previously been sharing with this hydrogen atom. And it's this HSO4- ion that goes on to accept the H+ that is substituted out of the benzene ring. Meanwhile, this H2NO3+ ion is involved in step 2, where actually all that happens is it falls apart into 2 pieces. And to do that, the covalent bond between the oxygen atom and the nitrogen atom, as I'm showing here, breaks. And it's the oxygen atom, with it being positive at first, that takes both of those electrons from out of that covalent bond, taking them away from the nitrogen, and this oxygen becomes neutral. And in fact, what it becomes is a water molecule, which is why the generation of the electrophile produces 1 molecule of water. Meanwhile, the nitrogen, which had its electrons taken away from the covalent bond in step 2, is now positively charged. And this NO2+ is the nitronium ion, the electrophile for this mechanism. During Friedel Crafts acylation, the electrophile is generated from an acyl chloride. There are obviously a huge range of acyl chlorides, but what they all have in common is they have this carbonyl group and a chlorine attached to the same carbon. And on this occasion, I'm showing a chain of 2 carbon atoms, and so this acyl chloride would actually be called ethanoyl chloride. Acyl chlorides themselves are actually weak electrophiles, but we actually convert it into something different, which is a stronger electrophile. And so if we show an equation for the generation of the electrophile, we start with our acyl chloride, and it reacts with something that is referred to usually as a halogen carrier. And that's got a really important role to play here, because what it does is it interacts with one of the lone pairs on the chlorine atom in the acyl chloride. And it's able to do this because the aluminium in aluminium chloride is actually electron deficient. It's only got 6 electrons in its outer shell. And so what it's able to do is accept a lone pair of electrons from the acyl chloride. And as that lone pair of electrons is pulled away from the chlorine as part of the acyl chloride in turn pulls electrons away from the carbon that is bonded to the oxygen within the acyl chloride. And so we can show this with curly arrows. We can show the curly arrow between the lone pair on the chlorine and the aluminium. That's showing a new bond is forming. And then we can show a curly arrow from the carbonyl to chlorine bond being broken, and the chlorine is taking both of the electrons within that bond. And importantly, this produces something referred to as an acylium ion. And this is a carbocation that's been generated as a result of this, and it is a much stronger and more stable electrophile than the acyl chloride that we had originally was. And not only do we generate the acylium ion, our electrophile, we produce AlCl4-. The mechanism for Friedel Crafts acylation is really similar to nitration. In step 1, our benzene ring is attracted to the electrophile, the acylium ion. And so the acylium ion attacks the benzene ring and a new bond forms, which we're showing with this curly arrow here. This leads to the formation of a positively charged intermediate, exactly the same as in nitration. And this is unstable because the delocalised pi cloud only has 4 electrons in it instead of the 6, which it needs to be considered stable. And it's also positively charged. And so it regains its stability by breaking the bond between the carbon and the hydrogen and taking those 2 electrons back into the pi cloud, topping it back up to 6 electrons, which is what it needs to become stable. And this turns into our acylated aromatic compound, which, if we'd used ethanoyl chloride, would actually have been called phenylethanone. And not only do we produce that, we also produce our hydrogen ion. As before, you wouldn't need to show this as part of the mechanism, but it's important to have awareness of what we're producing in this mechanism. And also, as with nitration, the catalyst is regenerated by reacting with the hydrogen ion that has been replaced. And so the hydrogen ion, which is highly reactive, reacts with the AlCl4- that was produced when we made our electrophile in the first place, and this turns into AlCl3, that's our catalyst being regenerated, and also HCl. And so in Friedel Crafts acylation, as well as our phenyl ketone, phenylethanone in this case, we also produce HCl as a byproduct. And so in general, in electrophilic substitution, there are always 2 steps. And in each of those steps, there is just one single curly arrow. And we also need to remember that there is a positive intermediate in any electrophilic substitution mechanism.